Happy Friday and welcome to the Friday Informatics Institute PowerTalk Informatics Seminar Series. I'm very happy to introduce today's speaker. Dr. Keren Lee is an assistant professor of mathematics at University of Alabama at Birmingham. He has a Ph.D. in mathematics from the University of Illinois at Chicago, and he specializes in statistical machine learning, distributed big data analysis, and bioinformatics. These approaches help us handle big data and allowing humans to interact with it and improving the ability to apply AI ML to a wide variety of practical settings. The title of this talk, Unveiling Collective Intelligence, Navigating Representative Learning for Federated Insights.
Okay, thank you, Amy. Thank you for your introduction. This talk is about my favorite research, distributed learning. In the past several decades, the world actually has experienced an explosive increase in different kinds of data. Some scholars call it the big data year, which influences people's everyday life in many ways. The term big data does not only indicate the growth of data, but also a new engine for economic development and social evolution. There are massive potential knowledge and insights mined in big data, which we cannot find in regular size data. Then, what is the definition of big data? Based on the definition on Wikipedia, big data primarily refer to the data set that are too large or complex to be dealt with by traditional data processing application software. In Emerson and Keynes' 2012 article published on significance, don't join in the data. They define data is large if it exceeds 20% of random access memory on a given machine, and massive if it exceeds 50%. In the earliest three-way definition, De Mono et al. Characterize big data by high volume, that is amount of data, velocity, speed of data in and out, and variety, that's a range of data type and sources. The complexity of a machine learning model fundamentally determines its representational capacity of the model, while the model quality depends on the amount of data, since it is built upon this data. High-speed data rates may introduce dynamic parameter change. Variety in big data refers to the structured and unstructured data. Unstructured data is unorganized and comes in different files or formats. In this presentation, we will only focus on high volume of data, that is large N. The first framework for big data I want to mention is the subsampling. Subsampling method samples a relatively small subset from the whole data set to perform analysis. The optimal spots to minimize variance of estimator is required such that you can put more weights on those spots for sampling. In 2014, Ma and Sun proposed leveraging techniques has been used to sample a more informative subset of the full dataset for linear regression problems. Inspired by de-optimality in optimal design theory, Wang, Yang, and Stafkin in 2019, they published a paper on JASA. That is an informative-based subsampling techniques called eyeballs for big data linear regression problems. Similarly motivated by optimality, Wang, Zhu, and Ma in 2018, they published another paper on JASA. This one actually developed an efficient two-step subsampling algorithm for large sample logistic regression, which is a special case of generalized linear models. Another framework is the divide and conquer. In 2011, Lin and Xi proposed divide and conquer method. Divide and conquer is a very popular method in both statistics and computer science. This actually is the early version of federated learning. This method actually first randomly partition data, then feed block by block, and aggregate those feeds. Complexity of this problem is still the same as the full data, but it allows parallel computing and with very high accuracy. While the distribution similarity between nodes or we say blocks are required to guarantee the accuracy, and the accuracy highly relies on the block size, that is n divided by k. K is the number of nodes, which really depends on the computer memory. But in practice, we should not expect our data actually is a single file. Sometimes you may not be able to handle it with your desktop. Usually, the data set is distributed, stored in multiple files, computers, servers, or even different companies, different countries. Within each data block, data points have a sort of similarity in some fields. We call it homogeneous partition. That is, homogeneity in coverts within block or node, but heterogeneous between nodes. This actually does not satisfy the justification requirement of divide and conquer or federated learning and most of the method. So array partition sometimes is needed, but such kind of intensive transmission will not be feasible. And the characteristic of distributed learning has three important things. First one is distributed, massive distributed. That means the k number of nodes could be large. Another one is a non-iid. That actually means heterogeneous. Another thing is unbalanced. That's similar to heterogeneous. That is, we may have lots of data in one node, but has very few data in another node. In this scenario, actually we will have some kind of issues. First, if we have a very low variation in some local features, we will not be able to update gradient search locally. And if the bulk of data loads are small, I'm not talking about the number of observations. I'm talking about the bulk, the convex bulk. If the convex bulk actually is small, then you will get high variance when you merge those results together. And the heterogeneous actually leads to the order of sequential updated matters. And we also have another issue. That is, the network bandwidth could be very low. Since in that way, it's very difficult for you to communicate a lot between nodes. Another very important issue is data localization and privacy. In that case, you cannot transfer your data, your raw data, to another node or to the central server. So in that case, lots of methods will try to get summary from the local nodes, then just convert this summary, or we say statistics, to the central nodes. Federated learning is a one actually try to solve the above issues. The idea of federated learning actually is almost the same as the divide and conquer. The only thing different is the distributed data actually has already been decided. And at each node, we have to calculate some statistic sent to the central server, and the central server just broadcast its result to the local machine. Then the local machine will try to utilize this system information to regenerate its statistics then send to central server. In that cases, we can repeat this procedure until we achieve some very good results. And there are some lots of papers work on identical distributions for either convex problem or non-convex problem, and there are some attempts for heterogeneous convex and non-convex problems. But I will say they still have some kind of issue when they facing the challenge of heterogeneous problems. A typical algorithm of federated learning is a local SGD. The local SGD actually try to get a mini batch from local data, then use this mini batch to update the gradient. When this updated the gradient, then we can update the coefficient we want. Then after several time points, we just send your updates to the server. The server will average your updates, then send back to all the clients and repeat this procedure until we get converge or stop at some time steps. Well, I think the major drawback of federated learning is this one heavily relies on SGD. That is, we have to calculate the gradient, but the gradient is something can help you to figure out what is the optimal point. This is like sufficient statistics, but this is like summary. This is not details of the local data. But for nowadays, our job is very complicated. We may want to have multiple tasks for some data set. In this case, a single summary is not enough. So how can we deal with such kind of circumstance? Actually, I propose representative learning. This is a method can deal with distributed learning. Okay, now let's look at federated learning. Suppose we have a data set D that is in a heterogeneous partition. At node K, we have the local data dk. And the number of K could be very small, much smaller than n. It could be large. If K is large, then that will reduce the accuracy of federated learning. The idea of representative learning is trying to construct a pseudo data point from the local data. Only depends on the local data. We call this a pseudo data point representative, xk tilde, yk tilde. Then we just send this representative data point to the central server. At the central server, we feed on this weighted representative data set. Why I say weighted? Because you need also carry the information of a number of observations at each node to the central server. In that case, we can get some coefficient beta, then broadcast the fitted results beta back to loads, then repeat this until we get further result. Looks like this is very similar, similar to federated learning, but the big difference is we don't use gradient. Actually, we use some pseudo data points with the same format as the original data points. So in this case, this pseudo data points will be very informative. The advantage of this representative learning is these representative points, since using the same format as the original data points, this will be interpretable and intuitive to human being. So domain domain science expert should be able to explain what happened when they get intermediate result. And another advantage is this data set should be, the final data set, the representative data set should be much smaller because this only depends on the number of load. So we actually did the data reduction. And during this process, we don't exchange any raw data, but some pseudo data points that is representative. And this one, since only relies on the local data, so it's born for parallel computing. And this approach actually prefers homogeneous within node. That is what actually happened in practice. Let me explain what is homogeneous again. For example, if you consider BMI, if you get a BMI from 3 different hospitals, like junior hospital, senior hospital, or regular hospital, you should not expect their BMI distribution are very similar. For example, I believe the junior hospital has a BMI pretty close. Their distribution, this covert actually is homogeneous within node. So in that case, you will get a very high variance if you try to merge the gradients together later. But for the representative learning, well, actually we do prefer homogeneous case. Then what is a possible way to construct pseudo data points? I think there's some very naive way. For example, central representative. The central representative can do those ways. First, we just split the feature space into some grid partitions, then just take the middle point of the feature space. In that case, we don't even look at the data set, and we will get this result pretty fast. But the drawback is this: the accuracy of this method is not that good. Another way is we just take the median of each covariance, median of each features. Or we can take mean of each features. And for representative response, we also take the mean of a response. For the mean representative, we name this one MR. This one actually has been proved works very well on linear models. And if you have a very small bulk for local data set, then MR can even work for generalized linear models. Why this one works well? Because of this, the property of mean representative. The mean representative actually is an unbiased estimator. So that actually means this one is very good in some means. Then we look at the variance of this estimator. The variance of this estimator actually is pretty close to the full data estimate. Beta hat deload for full data estimate. Beta tilde MR deload for the MR estimator. This distance is controlled by delta square. Here, delta is the maximum bulk of local data points. We also deload delta tilde as the representative coverts away from the local data bulk. So that is when the delta is small, then the variance of MR is pretty close to full data. So that's why this performs very well, and this one sometimes can even match with the full data estimate. But sometimes we may have a load with a very large bulk, and the model is not a linear model like generalized linear model. How can we deal with this? Then we propose another representative choice called score matching representative for generalized linear models. For generalized linear models, we assume the response Y follow exponential family distribution with the mean with mean mu. Here the mean mu is linked to linear predictor xi transport beta. We call linear predictor with a function g. This is called link function. So the log likelihood function is given by this format. Okay, we just try to maximize this log likelihood function. To maximize this log likelihood function, we need to set this derivative to be 0. That is score function. We need to set the score function to be 0. The score function of a log likelihood of a generalized linear model can be rewritten in this form. Here, this uppercase G is the inverse function of a link function G, and the nu here is a G prime divided by variance of response. For common use generalized linear models, we can have the nu and the G, so we can have a S here. Once S equals 0, then beta is the one we are looking for. So the idea here is pretty simple. Since our target is S, how about we do this? We just construct pseudo data points carry the same score function values as the local data points. In that case, when you put all the representative data points together, the score function values they carry is the same as the full data points. So if some beta achieves 0 at full data points, that one will also achieve 0 at the representative data points. So the procedure of this representative called score matching representative is like this. We get some initial estimate from MR. In that case, we can evaluate score function values for each data block. Once we get the score function values, then we can try to construct a representative to match the score function values load by load. Then send everything to the central server. Central server feed on this representative data set. Then broadcast the fitted value back to the loads. Repeat this procedure if needed. Okay, now is the technical points. Let me finish this pretty fast. For equation 4, the left-hand side is the score function values carried by K node. Right-hand side is the score function values contributed by representative of node K. We just want to solve this equation, but unfortunately, how many equations we have? If the dimension of x is p, then we have a p equations. But how many unknown variable we have? We have a yk, this one unknown variable, xk tilde, this is a p unknown variable. So we have a p plus 1 unknown variable, but p equations. So that means we have infinity solutions, and it's difficult to guarantee convergence. So what we are going to do is we take yk tilde as a weighted average of yi's of this form. Once we do this, then put this yk back to yk tilde back to equation 4 and multiply by beta on both sides. Then we will turn equation 4 into this. Since yk tilde equals this expression, then we can replace yi's on the left-hand side of equation 6 by yk tilde. Then we can guarantee the equation 6 always has a solution of eta k tilde. Once we solve out eta k tilde, then just take it back to equation 4. Then we can solve x k tilde. So that's the procedure how we solve score matching representative. Well, for the score matching representative, SMR, we did talk about the property first. Actually, for generalized linear models, as long as your your representative response is the mean of a response, then your beta tilde, the one fitted on representative data set, should be very close to beta hat. That's a full data estimate. As long as your delta tilde is small. Here, the delta tilde is how your representative converts xk tilde away from the local bulk. Okay, that actually means when your local bulk is small, then representative method will be good. Now let's look at the SMR. SMR actually take representative response weighted mean, not mean, but this can be written as mean plus some big O over delta tilde. So actually under the same condition of theory 2, SMR should be pretty close to full data estimate when the delta tilde is small. Another good property of SMR is for every iteration, SMR improve this is estimate controlled by delta tilde. That is, when your delta tilde is in a moderate size, then SMR will converge to beta hat pretty fast. Well, let's look at some simulation result. This simulation actually builds on a logistic regression. We use several kinds of different distribution of X. I mean, different distribution of features. We use mean zero normal, unequal variance normal, and beta distribution. In those simulations, SMR shows pretty close to full data estimate, while the MR and the joint counter are away from those results. Here I should mention this divide counter, since this one does not need sacrifice any accuracy. So its accuracy usually much higher than regular federated learning method. So since SMR is better than divide conquer, so basically it is better than most of the federated learning in terms of accuracy. Another thing I want to mention is big data property of SMR. Actually, we try to check if SMR can get additional benefit when the sample size N increase. When we increase the sample size, we figure out for all the methods, they actually benefit from this increment in the sample size. But only SMR get closer and closer to the full data estimate if they compare with the true beta. In simulation, we know the true beta, right? So to know how much additional benefit SMR get from this increasing in sample size, we just compare those methods with the full data estimate. That is, calculate this rooted MSE from full data estimate beta hat. In that case, we can say when N increases, all the methods actually just a horizontal line. That actually means for other methods, they cannot achieve additional benefit when N increases. But for SMR, when N increases, this one gets closer and closer to zero. Zero is a full data estimate. So we claim that SMR actually has a big data property. That is, even if you fix a number of distribution, you fix a number of loads, and increase the observations, SMR will get better and better and closer to the full data estimate. Now let's look at an application. We just use this famous on-time performance data for United States domestic flights from October 1987 to December 2019. There are 387 files on distinct months and years. That means the distribution of coverts on each file are very different. So they are heterogeneous. So we just assume those files are those. Here we consider 5 variables. The first one, arrival delay. This one is our binary response variable. When this one get delayed 15 minutes or more, this response will be 1, else that will be 0, and we have other 4 coverts: quarter, day over way, departure time block, and distance. The first 3 actually are categorical data. The last one is continuous data. Then we tried on 60 months data, 120 months data, 240 months data, and 387 months data. We try to compare those 2 methods with full data estimate. But unfortunately, those data are too large, so my computer cannot take care of the full data estimate. So I only have a full data estimate for the first 2 cases. But based on the comparison, you can see both MR and SMR has a very good MSE away from the Oracle beta. So in that case, it shows how good is the SMR and MR. But if we try to increase the contribution from the only continuous variable distance, this result could be slightly different. In that case, MR is still comparable to full data estimate, but the MR will get a very bad result. This reason is very simple. That just because when the uppercase G, the inverse function of a link function G, is very steep. In that case, MR will not be performs good. But when the contribution from continuous variable is small, MR can still be used. But when the contribution from continuous variable increases, MR does not work at all. So SMR can still match with a full data estimate. But for Poisson models, Poisson is another generalized linear models. SMR, the first 2 iterations of SMR performs not that good. But after 3 iterations, SMR can still comparable to full data estimate. Well, for this method, SMR Square-matching representative, let's make a small summary. First, SMR enjoys big data property. We have talked about this in the simulation. And the time complexity of SMR is essentially NP. So that actually improve the full data time complexity a lot, because for the full data estimate, the time complexity is NP squared. Another good thing for SMR is the underlying representative data set is greatly reduced to match the number of load K, while necessary load fitting information is preserved. And for the representative is a pseudo data points in forms of original data set. This is more informative than gradient and other sufficient statistics. So this one can be easy to understand and can make the real conversation between nodes or between the nodes and the central servers. Parallel, for the SMR, this one actually is first for parallel computing, and the conversation between nodes are pretty low, and we only require very small transmissions without raw data. So this method satisfies the data localization and the privacy concerns. Another good thing for representative data set is we can use the representative data set for further inference purpose, since representative data set is in the form of original data set. And we can also send the representative data set to other nodes. Once we send representative data points to other nodes, for other nodes, they can utilize these representative data points, treat it as a real data, mix with their own local data to do some local analysis. So that's the pros of SMR, but there are some drawbacks of SMR. First, original SMR has a non-constant intercept representative. It actually goes against the intuitive intercept. Such artificial non-constant terms not plausible model interpretation in downstream analysis, so hindering further inference. And another drawback of SMR is when we solve out the representative linear predictor eta, we guarantee there is a solution. But for generalized linear models, there are up to 2 solutions to that equation. So that will lead to some kind of unstable or high variance after you send the representative to the central server. And because we need to solve the equation of linear predictor, that one usually does not have an analytic solution. So we only have a numeric solution. So we have to request additional computational time, and that sometimes leads to instability. So because of this reason, sometimes we cannot get converged for some extreme cases. Then we try to improve SMR in 2 follow-up works. First, we try to split the original data loads by the information of a response and the information of linear predictors. For example, we can just split as the sign of etas. That's a sign of linear predictors. That will make valid representative of response. And we can also split the sign of a difference between y and its expectation. G is the expectation of y. In that case, we will get valid representative of a linear predictor. We can split at 0 points of S prime. Here S is the score function, but use eta as a variable. In that case, S eta will be strictly monotone. So we will have a unique solution of eta that will reduce the stability or instability of the original SMR solutions. We can also split the sign of response for binary models. Once we do this, then we would be allowed to utilize SMR to calculate AIC and BIC. So we can use this to do model selection based on the likelihood information to do model selection. In another paper, we reformulate SMR by forcing intercept representative as a constant. By setting intercept representative to be constant 1, it avoids prediction of nothing in explanation and escapes the case of losing representativeness of covert representative in SMR. Now, based on those informations, this is the true algorithm for SMR. So first, we assume we have a distributed data set, xk. K is from 1 to uppercase K, and we have a time step T. At the very beginning, we do mean representative. Once we do mean representative, then we can utilize the mean representative to calculate the square function values. Then we can do SMR. For mean representative, we first calculate mean of each variables. Then send this mean of each variable from local to the central server C. At the central server C, we just calculate the beta theta from this initial representative data set, then broadcast this beta theta back to all nodes. Once those nodes receive the first beta theta, then they can calculate score functions. They can calculate linear predictors eta. Then for each node, they can do further split by eta values, by y's, by lots of quaternions. Then we can calculate y theta, eta theta, x theta with the previous equations. Then we have the weighted representative. We send this weighted representative to the central server. At the central server, we just do the regular generalized linear model regression. Then we can obtain the beta theta back to all nodes, repeat until step size T. Then finally, we will get beta theta and representative data set, D theta. Okay, so this is the score matching representative. For my current project and the future project is like this. Currently, we are trying to extend this method to support vector machine. Support vector machine is a very interesting machine learning tool. This one has a non-smooth object function, but SMR require square function values. That's the derivative of object function. So that is, we cannot use SMR directly on SVM. And SVM in its solution, it only use the separate vectors. So this one is very interesting. Actually, we have achieved some significant progress in this project. And we also have another project that's a human in the loop. We try to use the representative framework to construct a human AI collaboration framework. Here, the human actually serve as a local and global decision makers, and the representative data sets from the AI local nodes helps human beings, helps the domain science expert to understand, interpret, and use their sense of intuition and reasonings to make decisions. And we are also trying to extend the structure of representative to decentralized network or probabilistic network. We are almost done with this project, and currently we are still working Well, we also work on online updating extension of representative. We have some idea of this already, but we have not finished this project yet. And I'm also looking for collaborations on applications of representative learning. If you have any distributed data set, you have a data privacy concern, you have a data localization concern, then I believe the representative learning should be a very good tool for you. Besides, representative learning is a method allows nodes and centers to do informative conversation rather than single sufficient statistics or gradients. Okay, thank you. So do you have any question?
Yeah, thanks for the talk. If anybody has any questions, feel free to unmute yourself. We're all friends among here, or you can also put your questions and comments in the chat. I was kind of, what are some? Yeah, can you elaborate on your future plan work? I was looking a little bit at your lab site, and I didn't see a whole lot of detail, so I'm just wondering what's coming.
Yeah, well, first we are trying to develop SM version of a representative, and we try to extend this to decentralized network and online updating, and we also apply this on human in the loop application. And I'm still looking for more collaborations on this framework. This is actually an alternative framework of federated learning. If you believe federated learning can do your project, this one can also do this, and maybe in some meetings can do better.
Do you have specific themes, fields, or kind of people that you'd be looking for the collaborators?
Well, I don't have any specific preference, but this should be good for hospitals. For example, if you have data from multiple hospitals, then they may have data privacy issues. If they said their data should not leave their own server, so you may have to generate some summary from the server, then send to your own computer, then you analyze those data on your own computer. So if you use this representative learning approach, then you can get some representative data points from the hospitals. Then you can just work on this representative.
I'm not sure that this is Dr. Barnes here. Can you hear me?
Yes, I can hear
you. So I got little fragments of interest in what you're doing. I do something called metabolomics, which generates very large data sets. And there is a sort of the community has a program that's used. It's developed by people at Riken and at UC Davis. It's called MS Style. We've been doing studies with about 600 data sets collected. Each data set is probably about 1 gigabyte in size. When we run it on our machines, we find that the machine is using 75% of its capacity. So it sort of fitted into some of the things that you said at the beginning of your talk. But it takes about 2.5 days to on a instrument with 32 gigs of memory, internal memory, and a terabyte of SSD.
Well,
but
I think
I was at,
yeah,
go ahead.
I think
Go-
your
go-
data set is the one I'm looking for.
Yeah. I was at a national meeting complaining about this, and a colleague who used to be at Emory, he's now at Jackson Labs, came around and said that I've got a new program, which is called Asari. It's written in Python, and it did the whole analysis in 10 minutes. And I'm not terribly sure what goes on under the hood, but perhaps you and I should talk a little bit more about this. It might be very interesting to pursue.
Thank you for the information.
Okay, I'll check with you later.
Okay, thank you. By the way, my email is pretty simple, just KLI.
KLI. Okay.
Yes, UAB.
All right. Very good.
Any final thoughts, comments, or questions? I'm surprised nobody else took that combination of letters, but. Well, hearing none, I guess we'll start our weekend a little bit early then, 4 minutes early. Everybody, thank you for attending. Thank you, Dr. Lee, for your interesting talk, and we'll hope to see you at, you have his email address. Hope to see you at the next Power Talk. Have a great weekend.
Yes, Dr. Lee. This is Jim Semino. I also wanted to thank you for your talk, contributing to our series. So
thank you for your
take care, everybody. All right.
Yep.
Okay.
Anybody want to collaborate, get in touch with Dr. Lee. Right.
Okay.
Bye.
Thank you.
Bye.
Bye-bye.